Question 2. Here we see an aeroplane that is travelling horizontally in a straight line at constant velocity. Newton 1 tells us in these situations that we have balanced forces. So if we consider our aeroplane moving at a constant horizontal velocity v, what I want to do is draw a free body diagram for the aeroplane. So considering the plane as a point mass, we have the weight force acting vertically down, which we can calculate as mg. As we have balanced forces, it must be true that there is another force acting in the vertical plane that is equal and opposite to the weight force. This upwards force will be the lift force and is equal and opposite to the weight force. I can calculate the magnitude of this lift force by writing down the following equation. One point to note here is that I cannot write down FL equals FW, as these are vector quantities and they are pointing in opposite directions, but I can claim that their magnitude, the length of the vectors, is the same. Finishing off the calculation, using FL equals mg, I find that the lift force in magnitude is 25,500 newtons to 3 significant figures. Before we start the next question, if we go back and look at the free body diagram for part A, it's important to realise that there would have been some drag force acting on the plane against the velocity. So for Newton's first law to be true, if the forces are balanced, there must have also been a thrust force provided by the engine of the plane, Ft, and those two are in balance as well. Now for part B, drawing the free body diagram here is very important. I'll just mark in the horizontal and a line 10 degrees below the horizontal, because this is the direction our plane is now travelling. We're told in the question to assume that the lift force is acting perpendicular to the velocity. So that means the lift force is acting in this direction. So the key understanding here is, how do we figure out how large this lift force is? Is it much bigger than the weight force? Is it smaller than the weight force? Going back to Newton 1, constant velocity means we have balanced forces. That means vertically we must have forces balanced as well. So we're going to assume that the vertical component of our lift force is balancing our weight force. So now I've drawn in the vertical component of our lift force. So the horizontal component of the lift force must bring the direction of our overall lift force back to the green line. So now we can see the lift force acting on the plane, FL, as shown in our diagram. Drawing another vector diagram will make it easier to complete our calculation. So we see that we have our component of the lift up and the component of our lift horizontal. And if we add those two vectors, we get the overall lift. So we saw that in our diagram we have an angle of 10 degrees between the vertical and our lift force. And the key idea is the vertical component of our lift force is balancing off the weight force. Using the cosine relationship, we can write down that cos 10 degrees equals the vertical component of the lift divided by the overall lift. So we can solve now for the total lift acting on the plane. That is mg divided by cosine 10 degrees. So remember, it's mg because the vertical component of our lift force is balancing off the weight force. And we calculated that in part A, 25,500 newtons. So we get our final answer, the lift force is 25,900 newtons.